recording. We started this chapter last class, and this chapter was about rate of return and the rate of return analysis, okay? And we went over 3 definitions of rate of return, and those 3 definitions are really just 3 perspectives on rate of return, what it is, and what it kind of means, okay? And so the first one, just to refresh your memory, was about loans, right? So in the context of a loan, a rate of return is the interest rate that is earned on the unpaid balance. So every year you find your balance, and then you apply the interest rate to that balance, and that interest rate is also a rate of return, right? Because that interest is basically the bank's return on your unpaid balance, all right? And we saw that you can see this in the formula, the A given P formula, which we've already seen, and also in the loan table, which we've already seen in chapter 3, right? So here again, the payments that you pay account for 2 things. They account for the principal, the loan itself, and they also provide a return of 10% on the balance, on the outstanding balance, right? So you find the unpaid balance, and then you apply the interest to that, right? So this is a return on the unpaid balance. Another definition, which we saw in chapter 5 this time, was about the break-even interest rate. So this is the interest rate at which the net present worth of a project is 0. And so the present worth is 0, meaning the present worth of the inflows minus the present worth of the outflows is going to be 0. And you can see this here, right? So what does it mean for this investment to have a rate of return of 10%? Well, we saw that if you compute the inflows and the outflows, if you compute their present worths, we get equal values. And so the net present worth, inflow minus outflow, is going to be 0. And finally, we talked about this internal rate of return. And so this is very similar to the loan, but it's in the context of a project, of a company investment or a company project. And so once again, it is the interest rate that is charged on the unrecovered project balance of the investment, such that, of course, when the project terminates, the unrecovered project balance is 0, which was the same case actually in the loan example. And so here we actually use the same numbers as before, but the context is a little bit different here. So we're talking about a company project, and therefore this is the internal rate of return. But the table that we used was exactly the same, right? So again, you find the project balance, which is very similar to the loan balance. And so here the perspective is the company is lending money to the project. We talked about this, right? That banks and loans and also companies and projects, you can think of them as like being analogous to each other. They're very similar. And so again, when you apply 10%, when the rate of return is 10%, right? So basically the firm or the lender, the company that lends the money to the project, earns a 10% rate of return on funds that remain, the remaining balance, right? Internally invested in the project, right? And so internally, this is where the name comes from, the internal rate of return, or IRR, okay? Now, so that was where we stopped last class. So now we're going to talk about a few different approaches for finding a rate of return. In other words, if I give you a cash flow, right? So I tell you you have some sort of cash flow, right? And there's an investment cost maybe, and maybe I need to invest again, whatever, some sort of cash flow. And I ask you to find the rate of return for this cash flow, right? To do that, well, we need to recognize first of all that we have 2 types of cash flows, or 2 types of investments. One is called simple investment, and one is called non-simple investment. Okay, so these are new. Actually, we haven't seen them before, these terms, but they're very easy. We're going to see. They mean very basic things. Once we identify what the type of investment cash flow is, we have different ways of finding the rate of return. And so what are these ways? Well, first of all, you can solve it by hand, but only in some cases, right? Sometimes it's very difficult to find. So basically, again, what we're trying to find is I. You're given N, you're given a cash flow, right? You're given N, you're given all the A sub N's, right? All of this is given. And then I'm asking you to find I. Okay, so finding I by hand sometimes is possible. And we've seen this also in the Walmart example at the beginning of this chapter, where I just gave you a present worth, I gave you a future worth, I asked you to compute the rate of return, and then it's very easy to do it. I mean, we could take logs or lins of both sides, whatever, and then find I. But we can only do this in simple, or not simple, I shouldn't say simple since simple is used here, but in very easy or very special cases, okay? And we're gonna see what those are. In some cases, you need to do trial and error, which is, I mean, a natural way of doing things sometimes, right? I try a value, I then maybe adjust the value, and I keep iterating a little bit, maybe back and forth, until I find the correct I. And in fact, some numerical algorithms, even if you use software, they kind of do this, right? You have to specify an initial guess, and then the software is going to find it for you. And the software is actually the third technique. Some of them actually use, again, trial and error methods. Some of them maybe use more sophisticated methods, I'm not sure. But in that case, you can use software, and this can be anything from Excel. And we're going to see, at least I'm going to point you to a YouTube video, which you can watch to know or to understand how you can use Excel. But it can also be any sort of optimization software, right? That even MATLAB maybe, to find basically the root of a polynomial we're going to see, right? So again, because the rate of return makes the present worth equal to 0. So if I write an expression for the present worth, set it equal to 0, then I need to solve for I, because the present worth is a function of I, right? So sorry, present worth is a function of I is equal to 0. So I need to find this I, and basically I'm finding the root of some polynomial. Right, so that's why you can use optimization software, but Excel is also very handy, and it gives you the solution using a function that's built in, okay? Or you can also use goal seek, again, so you can do many things here. So you can use Excel using a function that I will tell you later, which is specific to this case, or you can use goal seek if you want, right? So you search for the value of I that makes this expression that you have put in the cell, right, is equal to 0. I guess you can also do that. Right, so there are different ways, and let's go over them one by one. But first, let's talk about what a simple investment is and what a non-simple investment is, and what the difference is. Right, so what is a simple or a conventional investment? So if I give you a cash flow in which the initial cash flows are negative, right, so some initial cash flows are negative, and there's only one sign change in the net cash flow series, right? So assume that what I give you is a net cash flow, okay? So if I've already subtracted, there's only one arrow at every time point, right? It either points up or it points down, so it's a net cash flow. If the initial ones are negative, like I've drawn here, and then there's only one sign change, something like this, maybe. So notice here, this is negative, this is negative, this is negative, and now I change to positive, but this is the only sign change that has happened. Right? This is called a simple investment. And we're going to see, of course, a non-simple investment is something where you have multiple sign changes. Okay? But a simple investment looks exactly like this. And it can be one payment that's negative, and then all the rest are positive. But it can also be a few negative payments at the beginning, but then the sign changes and it stays positive until the end. Now, in cases where you have a simple investment, you actually have a unique rate of return. Okay? So this is why it's important to differentiate between these two. We're going to see later in examples why. So if I give you an investment that looks like this, you can know, because this is a simple investment, that there's only a unique, I'm going to call it I star. Okay, so this is my rate of return. This is I that I need to find, and there's only one value here. And so I can use whatever technique I want to find this value. Okay. Now let me erase this so I can demonstrate the other one. So a non-simple investment has more than one sign change in the cash flow series. So maybe I draw something similar to what I had before, but, well, just to make it a little bit more interesting, maybe something like this. Now notice this is negative, negative, negative. These are costs. The arrow points down. This is positive. This is negative again. This is positive, and this is positive, right? So here I had one sign change here. I had another sign change here. I had a third sign change here. So I have more than one sign change in my net cash flow series. This is called a non-simple investment. And the reason why it's important to differentiate is the following. In non-simple or non-conventional investments or projects, it is possible, but not always the case, that you have more than one rate of return. All right? Sometimes you will have a non-simple investment that has a unique rate of return as well. But in some cases, non-simple investments will have multiple rates of return, and then we would have to address those differently because of this issue. Okay? Note, if you have a zero cash flow, so assume this arrow wasn't there. So this is actually very interesting. I picked a nice example. If this arrow wasn't there, so there's no cash flow here, cash flow is 0 at this time point, I actually can ignore the zero cash flow, and then I've turned my investment into a simple investment, because if I ignore this payment here, these are all negative, and then there's one sign, well, I mean, ignoring the 0, and then there's one sign change here. So actually, if I ignore if this was 0 here, I can ignore it, and I've turned my investment from simple into from non-simple into simple. Okay, so this is just a note for you. Now, what happens when there is no sign change in the entire cash flow series? Okay, so maybe I should ask this to you, see if you have any input on this. So I give you a cash flow. So let me erase just so I can draw an example maybe. It's a kind of a weird looking cash flow, right? Everything is just income. Whatever, right? There's no sign change here, right? Everything is positive, or I can draw, I mean, alternatively, everything is just costs. What happens in that case? I mean, you can do it, you can answer either intuitively, conceptually, or mathematically if you want. So what happens, meaning what happens to the rate of return? What do you think is going to happen? Yes, Mazen?
Yes, it will be impossible to find the rate of return.
Exactly. So there's really kind of no rate of return in this case, right? And the reason why, you can think about this conceptually again. So if you look at the words rate of return, it means I get a return on something. And so usually what that means is I put money down for an investment, and then I get money back. So there has to be at least one sign change in the way I've said it just now for it to make sense. But if everything is income, I mean, I can't compute a rate of return if I don't have an investment, right? And if everything is a cost, I can't compute a rate of return if everything is just outflow, right? If I don't get some money back on this investment or on this outflow, right? So conceptually, you can see that there's not going to be a rate of return really. I mean, it's not really well defined in this case. Mathematically, I mean, it's also the same thing. Remember what I said about the rate of return? It's when the present worth as a function of I is equal to 0. In that case, what that means again is the inflows, the present worth of the inflows is equal to the present worth of the outflows from the definition, right? So if there's no sign change, then well, everything is either inflow or everything is either outflow. So I can't really get a 0 because I have to subtract to get a 0. But if everything is positive or everything is negative, I can't get a 0. It's just not possible. Okay, so even mathematically, you can see that it doesn't make sense, right? So that's just like an FYI for you. But most of our cases, of course, I'm not going to give you an example where I mean there's no point, right, to that example, right? I'm not going to give you an example consisting of all income, which I mean even in practice, like it's hard to think of an example where that would be the case, unless I deliberately exclude investments that were made before or something. I don't know. In any case, let's not dwell on this too much. All right, so now we know how to classify the investments. Again, here just a review, just to give you some more examples. So one sign change makes it a simple investment. So you see here, this is negative, this is 0, so I ignore it. Then positive, positive. So negative, positive, positive. There's one sign change, so this is a simple investment. And then in terms of rate of return, this ROR thing, it has a unique rate of return. Now what happens if the initial flows are positive? So if the initial first payments are positive, and then one sign change occurs, right? So something like this. So it's kind of the opposite of what I've drawn before. So in a way, it's simple because it has one sign change, but the initial cash flows here are positive. So it's the opposite of this definition. And the answer is, well, we call that, it has like a special name, we call that a simple borrowing cash flow. So again, it's like you're borrowing money, you're getting income, and then you have to pay it back. It's also simple in a way because there's one cash flow, but it's not really an investment in that case, right? It's borrowing. Non-simple investment, well, we saw that we have the initial cash flows are again negative, but there is more than one sign change in the remaining cash flow series. So you see here we have negative, positive, negative, and so therefore we have the possibility, not always the certainty, right? Just the possibility of having multiple rates of return. So here we have a few examples, and so maybe now is also a good time to get some like input from you guys. If I give you these three projects, let's start with the first one, project A. This is the cash flow for project A, this column. What type of investment is this based on what we just defined? And of course, why? Yes, Mohammed?
Symbol, because there's one sign change.
Yes. And the initial cash flows, of course, are negative, right? Just to complete the answer. But yes, you're absolutely right. First few cash flows are negative, and there's only one sign change. It goes from negative, negative, and then it switches to positive, and it stays positive. So this is simple. What about project B? Someone else, maybe? Okay, you can go ahead, Mohammed. Yeah.
Non-symbol, because we have two sign changes, and the first one's negative.
Yeah, so yeah, initial cash flow is negative, and then we go positive, negative. Actually, we have, well, 1, 2, 3 sign changes, really, right? Because negative to positive, positive to negative, and then negative to positive again. But yes, you have more than one. That's the important thing. Yeah. And yes, so go ahead.
Yeah, I said yes. Sorry.
Oh, okay, yeah. Yeah, but the important thing, again, is that we have more than one. I mean, the number doesn't really matter that much, okay? But yes, so this is non-simple. What about this last one? We kind of just covered the name for this. So these maybe I should. What about C? I mean, maybe just if you don't remember the name. Yes, so Mazen put in the chat, it's simple borrowing, and that's absolutely right. And the reason why is because the first one is positive, and then the rest are negative. So there's one sign change, but the first cash flow is positive, okay? So this is simple borrowing. So this is maybe just a quick exercise about how to distinguish between them. So again, A is simple, B is non-simple. Both are investments because the first initial cash flow is negative. And then C is simple borrowing because the first initial cash flow is positive and there's only one sign change. Now, if I take these projects and I graph, if I do the following, before I reveal that, actually, let me draw it here. If I graph the present worth as a function of the interest rate, and we did this in chapter 5, if you guys remember, okay? What are they going to look like? And I'll show you what they look like. And we can see the differences between, for example, the simple investment and the non-simple investment in particular. So let me erase the pen and show you what these graphs are for these cash flow examples. So if you look at project A, right, this is very similar to what we've covered in chapter 5. The graph looks similar, right? It crosses the x-axis at this point, right? And so this is the point I star. And so that is the point where, by definition, so actually here there's a star, right? The present worth is equal to 0. And therefore, this is a rate of return. And notice, because this is a simple investment, there's actually only one. So the graph is such that the graph is only going to cross, or the plot of the function is only going to cross the x-axis just one time. And therefore, we have a unique rate of return. And this is always going to be the case with simple investments, right? Now let's look at the non-simple one. Again, we said it's possible that it looks very similar to this. It can happen. But in some cases, actually, maybe even more often than not, it's going to have multiple intersection points. And therefore, there's not actually a unique rate of return in this case. And we're going to see that this case is a little bit special, and we're going to do something different here. We're not going to be able to use, I mean, we are, but we need to modify it at the very least. But we're going to talk about that in the coming slides, so don't worry about that. Just know that this is non-simple, and therefore the graph looks actually kind of funny and kind of weird in a way. But that's because, I mean, this cash flow looks kind of funny and kind of weird. If you look at project C, it's a simple borrowing cash flow. Why? Because, again, the first one is positive, and the other ones are negative, and there's one sign change. And you can see here is kind of the reverse of this, or the mirror image of this. So the present worth actually goes in the opposite direction, but again, it only crosses the x-axis one time. And so we're actually not going to be dealing with this a lot. Maybe, I'm not sure about the homework, but in the examples in the slides, we're not going to talk about simple borrowing a lot. Most of our talk is going to be about simple investments and a little bit on non-simple investments. But simple investments, hopefully you agree that they're more common in real life, right? You put the money down and then you start getting returns. But in some cases, you need to put money back again. Like non-simple investments do happen, right? And we're going to see examples of that later. In fact, one example we've already seen in chapter 5, but not directly. also in chapter 6. But you'll see what I mean maybe when I get to it. It's about the cycles. And you'll see when you stitch multiple cycles together, sometimes you will have a negative, right? You will have positive, 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 negative because you're restarting the cycle. That's just sort of FYI, but it's coming later. All right, so now let's talk about the methods that we use to find the internal rate of return. So again, we highlighted 3 methods. We're going to go through them one by one. First is direct solution. And again, I told you that you can solve it using math, right? You can solve it analytically, but only in special cases. And what are those special cases? Well, the first one is when you have a two-flow transaction. So basically you have a P and an F. Right, so you have just one transaction here, another one here, and that's your entire cash flow. In this case, you can actually solve it by hand. And just to remind you, this was the Walmart example that we've seen at the beginning of this chapter. We have P for the stocks, and then we had the F, and we were able to use our F given P equation, or P given F, whatever, right? But I think the one we used was F given P, and we solved for I. Because N was given, everything was given, we just needed to solve for I, and we did it using math. And we can do that because that was an easy case or a special case. The other case, or the other example, let me just, actually, I can just draw it here, is when you have up to 2 years of return. So let's suppose you have a P at time 0, and then you only have 2 years, 1, 2. And you can have cash flows in both of those years. This one you can also solve by math, by hand, right? And the reason why is because if you think about it, and we're going to do this in an example, if you move this back, again, you're trying maybe to solve this equation from the definition, right? This is what you want to solve. So you need to, first of all, compute the present worth by moving these payments back. Because you only have 2 time periods, the largest exponent you can have for 1 plus I is going to be 2. Or negative 2, I mean, it depends. But I mean, if you're going to compute the present worth, right, you can also compute the future worth if you want. It gives you the same thing. Right, you can solve it either way. So it just depends on what you want to do. But let's assume we're going to use the present worth. So the largest exponent, well, I mean, it's really -2, but we're going to see how we handle that, okay? But it's because of this 2 that we get a quadratic equation, and we know how to solve quadratic equations, okay? But in general, if I add one more time period, you're going to get a cubic equation, and that becomes a little bit more difficult to solve for I, in that case, by hand. And of course, if I go to 4 or 5, you can pretty much, as New Yorkers say, you can forget about it, right? The other method is a trial and error approach. And so this is used for more complicated projects, but maybe not too complicated that you want to have to use software. So this is kind of an in-between approach. And so in that case, you can guess a value, see what you get, what the present worth of it is. Is it 0? Good, then stop. If not, then you need to iterate. You need to make some adjustment to the initial guess. And you proceed until you find the I star that you want. And lastly, using software, again, like I told you, you can use any sort of mathematical software. I mean, Mathematica, Wolfram Alpha, whatever, MATLAB, numerical packages in Python, whatever you want. You can use that to find the internal rate of return, or you can just do it using Excel. So let's go through these one by one and see examples. So let's start with the direct solution method. So I'm asking you here to find I star using the direct solution method. Again, so this is using it like doing it by hand. So I give you 2 projects. First one, notice how what it is really. I mean, it really is just an investment at time 0 of 3,000. And then at time period 4, I get income. So there are only 2 transactions here. So therefore, I can very easily solve it by hand. What about the second one? Well, the second one has 2,000 at time 0, right? And then it has 2 other cash flows. So it has 1,300 here, and then 1,500 here. Sorry. Right? So this is 1,500. But because there are only 2 time periods, I can also do this. So it's either or, right? So it's either 2 transactions or up to 2 time periods. You can do either of them by hand. And so let's see how we do the first one, right? So the first one, we've already done it before, so I won't spend too much time on this. We've done it in chapter 2, and we've done it at the beginning of this chapter. So here, notice what sort of equation I used. I used the F given P equation. So this is my F, this is my P, right? And then I need to solve for I, given that I have 4 years, because the cash flow, right, was 0 and then 4. And if I do that, I just manipulate the expression in order to solve for I, and you need to use lins and stuff, or logs like we've seen before. Hopefully you're all comfortable with that, and at the end you get a unique rate of return. Why is it unique? For project 1?
Because it's simple. Because
yes, because this is, yes, exactly, because this is simple. Therefore, I have a unique rate of return, and that's exactly what I get. So that's great. What about project 2? So for project 2, it's a little bit maybe more natural to solve it using, again, the equation that looks like this. Now, actually, you could do the same for 1 if you want to. It's just maybe easier to use the F given P equation. So in a way, for project 1, we kind of used the future worth. Right? We set it equal to 0, in a way. I mean, you could think about this later if you want. You may be wondering like why we do something different for 1 than for 2, as I'm about to show you. But it really is the same. It's just that here it's so easy that I can use my F given P equation. But even if you write it as future worth or present worth is equal to 0, as we're going to do for project 2, you're going to get the same answer. It's just really just moving things around. Okay, so for project 2, as I was saying, you want to solve this equation here. Or you want to solve the future worth of I star is equal to 0. You can do it either way. But the way the book does it, and the way most of the time we're going to do it, is using present worth. And so let me write that. Okay, so yeah, obviously I'm showing you the whole thing, but let's go step by step. So I write that the present worth is equal to 0. I need to move the cash flows to times 0. So this one is already at 0. These ones I move to times 0, right? And you see here I multiply by 1 plus I to the minus 1, or I divide by 1 plus I to the 1, and here 1 plus I to the 2. Right? Now what I'm going to do is I'm going to substitute. I'm going to make a substitution. So I'm going to say let x equal to this thing here. Right? This. Now if you do it using the future worth, you don't need to make this well, you need to make a similar transformation, I guess, but you don't need to make this exact transformation. You still have to, I think, make a transformation because you're going to set x as equal to 1 plus I in that case. But in this case, you set it to be equal to 1 over 1 plus I. What that means is I can rewrite this expression that I have here. So let me erase the pen so you all can see what's happening because it's getting a little bit messy. You see here I just rewrote the expression using the substitution that I made here. Now, of course, what type of equation is this? Well, this is a quadratic equation, right? Constant term, and then I have something multiplied by x and something multiplied by x squared. And so how do I solve this? If I want to find x, actually, just to maybe make it a little bit more clear. Yes, quadratic formula. So hopefully the answer maybe was too obvious that you all were wondering like why I was asking you that to begin with, right? But that's exactly right. So I need to use the quadratic formula to find x. So x is going to be equal to, let me see if I can get this right. It's been a while. Hopefully, if you don't know what the quadratic formula is, this rings a bell now. Assuming I did it, I wrote it correctly, right? Divided by 2a. Okay, so I need to use this formula in order to find the possible values of x's. Now, in general, just maybe as a mathematical point, notice here that I have a polynomial of degree 2, okay? You can imagine, of course, if I had more time periods, if I had 7 time periods, this is going to go up to 7, right? I'm going to have, assuming we have cash flows at every time period, I'm going to have something times x squared, something times x cubed, something times x to the 4th, etc., all the way to x to the 7th. And so first of all, that's why you can't do it by hand. We don't know how to solve an equation like that by hand. But also, we know from math, using the fundamental theorem of algebra, that any n-degree polynomial, so hopefully you guys remember this, has up to n complex roots, right? If you count them with their multiplicities. So I'm not going to go into detail like what is multiplicity if you don't remember, but those of you who do remember maybe would appreciate this perspective, maybe a little bit at least. Okay? So there's a question here. Of course, I mean, notice here that what I'm saying for this specific example is that I'm going to have up to 2 roots if I count them with their multiplicities. So there may be the same root, but it appears twice, but it may be 2 different roots. But if you look at this cash flow here, hopefully you all agree that this is a simple cash flow. So how can I have two roots potentially? But this is like, I'm saying that because it's a simple cash flow, you have a unique rate of return. And the answer is, well, in this case, if I solve for x, let's see what do I get. So if I use this equation, I get two possible solutions, right? One is x is equal to 0.8. One is x is equal to minus 1.667. Now, I'm not done yet because I haven't solved for I. I need to go back here, and I need to find I given the values of x that I just found. So if I do that, I plug back in here, I plug back in here, and I find I. I get that I is either equal to 25% or it's equal to minus 160%. Now, this one is okay, right? And a rate of return of 25% makes sense. At least, I mean, it's possible, and it makes economic sense, I guess, because intuitively, it's a valid rate of return. But what about this rate of return of minus 160? Well, we'll see what this is saying. So this is saying essentially that I'm losing all of my investment plus 60% more. So I'm losing my principal, but I'm actually losing more than the principal, which really, in the context of an investment, does not make a lot of sense. So that's why we're going to restrict ourselves to only looking at interest rates that are between minus 100%. So it's possible that you lose all of your principal, right? That's completely okay. I mean, it's not okay economically because that's not good, but it's okay mathematically, right? It can happen. It's also possible that you go up to infinity. So why is it not just up to 100%? Why can the interest rate be 200%, 300%? Maybe I'll ask the question this way. If your rate of return on something was 200%, is that okay? Does that make sense? Yes, why? Like, what is it saying basically? Roughly speaking, I mean, I'm not asking you like in terms of present worth. Just I tell you that this has a rate of return of 200%. What does that mean? Okay, this is another obvious question, maybe not. But what I'm saying is basically the following. So let's see, there are some answers. Yeah, exactly. That's what I was looking for. You're getting double your principal. So it's absolutely fine if the interest rate is 200, 300, 400,000. Sorry, not 400,000. What is 400,000? 400% is what I meant to say. That's completely fine. However, it doesn't make a lot of sense for the interest rate to be negative 200% because that means you lose double your principal. And for investments, you either just lose the money or part of it, or you make money, right? And so that's why we're going to restrict our attention to interest rates that are in this region. So this interest rate here does not make sense, so I'll discard the solution, and therefore I get a unique rate of return in this case. All right. Is there anything else that I need to say here? No, yep, that completes the example. So again, we have a unique rate of return in each case because both are simple investments. And just to reiterate, we can do this by hand because these have special structures. Now let's look at a more interesting example where we can't really, before we do that, Mazen, yes?
Yes, Doctor. In project 2, can you give me, can you show me just the previous slide?
Yes, here.
Yes, and the cash flow on the right, if we use period 1 as the reference and equate it to 0, then in this case we don't have to deal with the quadratic formula. It is first degree.
Interesting. I'll have to think about that because I wonder if the definition, I mean, I don't see why not, right? Because you can use present worth, you can use future worth equal to 0. Like, why can't you pick any other time period and equate it to 0? Unless I'm missing something here. It should be fine. And in that case, maybe, yeah, I mean, I would try it and see if it gives me the same answer. If yes, then maybe that's maybe a smart way of doing things. I'm not sure why they didn't present this in the book, but that's a good point. I haven't done this myself, and I'm also just wondering if like the definition still holds. Like, I know for sure you can use present worth is equal to 0, you can use future worth is equal to 0. Can you use the present value at time 1 and set it equal to 0? I guess, yeah, because if the present worth at time 0 is equal to 0 and you move it forward by one time period, you're multiplying by 1 plus I, right? And so that's also going to be equal to 0. So I think it's fine. So yeah, good point. So I would just do it by hand just to confirm at least that it gives me the same solution. If you already did, great. If not, maybe we can do it later. But that's a good point, and then maybe you don't have to deal with the quadratic expression, which is handy.
Because
Thank you.
yeah, if
Yeah,
it's
go ahead.
if it's,
Sorry.
I think for 3 periods we can maybe do for 3 periods or 4 periods, because it said just projects for up to 2 periods, service life.
I see what. Yeah, I see what you're saying now. Yeah. So yeah, very good point. So thank you for that. I will maybe, if I have time, I'll try to do it by hand. Maybe, as you said, maybe consider 4 periods, and see if I can get away with doing it at time 2, let's say, because that means everything is going to be squared, and then maybe I can solve it even for 4 time periods, let's say. So very good point. Thank you. All right, so now let's see how we can use trial and error to find more complicated cash flows. Of course, assuming that we don't do what Mazen just said, which is worth considering. Okay, so let's just follow what the book says, right? So if you have a cash flow here, notice we have 3 time periods and we have more than 2 transactions. So obviously, this is not something that is covered under our special cases. And so this is the cash flow, and this is the cash flow diagram. So how do I do it using trial and error? Well, I mean, naturally, as always with these algorithms, first of all, you need to guess some interest rate. And so I'm going to guess 15%, okay? Then I need to compute the present value at, or the present worth at 15%, or at time 0 using 15%. So I compute this, so PW of 15%, right? And I find that it is this much. So that's basically taking all the payments of the cash flows, moving them back to time 0 using 15%, and seeing what the value that I get is. And it turns out to be this much. Now, of course, this is not 0 in this case, so I can't stop. I need to adjust and iterate. I need to do more iterations. And so notice here that this is positive. And so now the question is, do I increase I or do I decrease I in order to get closer to 0? And so I'm posing that question to you. Maybe if you guys can remember, even from chapter 5, what we should do. Think about the terms and the present worth. So if you have some payment here, right? In order to move it to its present worth, I need to do something like this, whatever n is, right? So, of course, if I add them all together, that's going to give me the present worth. Right, so in this case, if I find that the present worth is positive, should I increase it to get it closer to 0, or should I decrease I to get the present worth closer to 0? Yes, Khalid? Increase?
Yes.
Yes, exactly. So Shadi is also saying increase, and that's absolutely right. So if I increase I, so if the present worth is positive, I increase I, and that means basically because I here is larger, I'm multiplying, right, by something smaller. And so I'm making the present worth smaller because I'm discounting future payments more and more as I increase the interest rate. And so if the present worth is positive, I increase I. If it's negative, of course, I go in the opposite direction and I decrease I. And so here, I've increased the present worth from, the interest rate from 15% to 18%. And so I've gotten a value that's negative. And so I've kind of overshot the 0 point, right? So I went from positive to something negative, and so I know at least that the true interest rate, the internal rate of return, right, is somewhere between 15 and 18%. Now, actually, one thing we can do, so you can keep guessing, you can maybe adjust your estimate, right, and try again. So maybe you can say, oh, I'm going to try 17%, let's say, because obviously it's closer to, I mean, you could think about it, it's closer to 18%, more likely at least, than it is to 15% based on the values that I have here. So maybe I'll try 17%. I'll see what that gives me. And I keep adjusting like this. But you can be a little bit maybe smarter. And notice here that, of course, like I said, the solution is somewhere in between. Let me erase the pen. It's somewhere in between 15% and 18%. And notice here at 15%, I get this value. I get this point here. At 18%, I get this point here, which is the minus 749. Right? And I know this, I want somewhere between these two here, right? And you can be a little bit smart. Of course, the function may not be linear. Just maybe let me state that as a point. The function may look something like this. Sorry. I mean, this was not really a very good drawing. Let me try again, if I can make it a little bit more smooth. Not really. I overshot the point at the bottom. Okay, but you guys get what I'm saying. The function, in fact, the present worth function, as we saw in the examples before, it may not be linear. But you can still use linear interpolation to try and approximate the solution. All right? Can you guys hear me now?
Yes.
Yes.
Okay, sorry
Yes.
about that. Yeah, I just disappeared apparently. All right, so what I was saying was that the function itself, the present worth function, may not be linear necessarily. It may look something like this, which I was trying to draw, something like this, whatever. I mean, it should not increase here, so that was a bad drawing. But I'm trying my best to sort of hit these 2 points and give a nonlinear shape. So just imagine I did that correctly, okay? But you can still use linear interpolation to get a good approximation for the solution, right? And so is anyone here not familiar with linear interpolation? I hope you've all seen this maybe in a numerical methods class or maybe in math, so I don't have to spend time going over it. Anyone not familiar with linear interpolation? Yes, Mohammed?
Yes, not familiar with it.
Okay, in that case, maybe I'll just go in a little bit of detail. So let me switch to a whiteboard. So, wait, how do I do that? Oh, interesting, okay. Oh, from here. Okay, there we go. All right, so what is linear interpolation? So let me first draw the picture that we had. I'm not going to go into maybe too much detail, but hopefully I'm going to give you enough so you can like do the rest maybe yourself. At least I'm going to set you up properly, inshallah. So the picture that we have is the following. So here we have 15%, here we have 18%, right? And then for the other axis, so let me put the values that we had. So actually I should have drawn this maybe a little bit more to the right so I have space. So 3553 and then minus 749, right? And of course 0 on the y-axis is somewhere in between, okay? And so this point corresponds to 18%, and then this point here corresponds to 15%. And so obviously if I were to do linear interpolation, right, linear from the name, I'm going to assume that the function is linear. And so basically these 2 points that I found are part of a linear graph, right, a linear function. So I'm going to connect these 2. Now what I want, maybe I'll just use a different color, is I want the 0 value here. I need to find, basically my question now is to find the interest rate, which I'm going to maybe just refer to as x, because I'm in here I'm going to use x's and y's, but you can label it I or I star if you want. It's really I star, right? So this is what I want to find. This is what I don't know. And so because I have basically linear interpolation, what it does is you have 2 points. You assume the function is linear, or maybe it is linear. You don't have to assume it sometimes. In this case, we're assuming because the function may be nonlinear, right? And then you can use the 2 points to basically kind of find the equation of the line and then figure out what this point must be, right? Because if you have the line, and you have the y value, you can figure out the x value, right? Again, the equation of the line is y is equal to mx plus b. And so if in a way you found the slope of this line, this red line, and you know the intercept, you know what y is, the y that you want is 0, so you can solve for x. Okay, that's kind of what's happening here. We're not going to do exactly that, but that's what linear interpolation does. And the way mathematically you do it is the following. So let me maybe just use another color. So I'll use green. I'm going to label this point as y1. So actually green was a poor choice because it's very bright and maybe it becomes a little bit difficult to see. So let me use magenta. So I'm going to label this as y1. I'm going to label this as y2. I'm going to label this as y, okay? This is x, as we've seen, this blue one. This is my x1. This is my x2, all right? The principle, and I don't remember the formula for linear interpolation. I mean, you can always look it up, but I don't memorize it. I mean, one nice way of thinking about it is the following. What do I know from the picture? Well, I can be smart. I know that the slope of this segment here is the same as the slope of this entire line, because it's obviously just part of the line, right? And so let me see if I can use that to write an inequality, an equation, and then I can maybe solve for x using that equation, okay? So again, the slope of this small segment is equal to the slope of the larger segment. So what is the slope of the small segment? So let me pose this as a question to you guys.
M.
Given what I've written here, yes, m, but in terms of y's and x's, so maybe forget about this for a moment. I mean,
it is y1 minus y.
okay, I mean, you could do that, but let me, so I have it as the opposite, but let's see. So as long as the bottom part is correct, it will be the same. So over
the x's, which is 13 minus x.
Yeah, so in general, it's x1 minus x. So you're absolutely right. Okay, so this is the slope for the first segment. I actually have it written as the opposite, but it's completely fine to do it either way. I mean, you could do y minus y1 over x minus x1. These are the same thing, okay? So this is the slope of the first segment. What about the slope of the entire line, or the sort of between the 2 points that I found?
y1 minus y2, if we're going to continue the same way.
Yep.
Over 18 minus, no.
No, you're right. Or did you? No, yeah,
13,
the opposite. Yeah.
No, 13 minus 18, yes.
Yes, okay, yeah. So it is over x1 minus x2. Right? So this is basically what I described here by the slopes being equal. Now let's see if I can solve for x from here. I mean, and this is maybe where I'll leave it to you. And so after you know this, this is a good starting point for deriving the expression that we have in the slides. And so let's see first of all if we have everything. So obviously we have y1, that's given. Y is given as 0, so we have that as well. X1 is also given as 13%. X is my unknown, so I have one unknown so far. Y1 is given. Y2 is given, minus 749. X1 is 13%, X2 is 18%. So from here, you can manipulate this expression until you get something that looks exactly like what we have in the slides, okay? And this is how you interpolate. So basically find X on such that maybe if you evaluate X at this line, you get 0. All right, and so here I'll leave the rest of the computations to you guys, but hopefully what you end up with is this here. So let me switch back to, maybe just hit escape, is this thing here. This expression, I mean, you can see maybe y1 is here, right? y1, y2. This 3% is basically this minus this, so it's x1, I think, or x2 minus x1, right? And then here we have x1, right? You can see, I mean, the numbers are here. When you manipulate the expression, you should arrive at something that looks like this. You may have something that looks different, but at least it should evaluate to the same answer. Because as we said, like sometimes you can interchange things as long as you're consistent. So if we do that, we actually find using linear interpolation that our x is 17.45%. Now again, just to make sure we all are on the same page, this is an approximation because the function may not be linear necessarily. But I can use this to try and evaluate then the present worth at 17.45% and see what I get, right? And so if I get exactly 0 or very close to 0 within some tolerance, I can stop. If it's not exactly 0, or maybe it's like still way off, I can then maybe interpolate again to get a more accurate estimate. Because you can think about it like if the function is nonlinear, the smaller my range is, so assume I bracketed the point between this and this instead of 15 and 18. That's obviously going to be a more accurate, like even if I use a linear function, it's probably going to approximate the function better than if I fit a linear function like this, right? And so the narrower your range, the more accurate your interpolation estimates will be. All right, so let's see an example. And so in this example, I'm giving you some cash flow. I mean, there's a lot of talk here, but let's go. I mean, we really just care about the cash flow. So The project would require an investment of $10 million in assets, and it would produce an annual benefit of $1.8 million over a service life of 8 years. All right. And then when the project terminates, you can get $1 million in sales, or like in a salvage value. And I'm asking you, what is the rate of return? And please find it using the trial and error method. Maybe even if I didn't specify, but this was on an exam, since you can't use Excel, you obviously can't do it by hand, so you need to use this trial and error procedure. And so if you draw the cash flow, this is what it looks like. I mean, everything here is in millions, so they dropped the millions, right? It's just 10, 1.8 annual benefit, right? So you're given P, you're given A, and the salvage value at the very end. So this here is the total, right? It's 1.8 plus 1 million. And N is equal to 8 years. And so now we need to find the rate of return. And so we're going to use our trial and error approach. So our first step is always to start with a guess. So let me guess 8%. What do I need to do? Well, I need to find the present worth at 8%, see what that is. I plug in, I move the payments back, right? So I can be smart because I have an annual equal payment series. Let me actually switch to red. I like magenta. It's not a bad color. Right? And I need to move the salvage value back to time 0. And this is what I get. Obviously, this is greater than 0. So based on what we said before, I need to increase I to get closer to 0. So that's what I'm going to do, right? So again, if present worth is greater than 0, increase I. Right? And so I can try 12%. Now at the moment, of course, I can't interpolate quite yet because I haven't bracketed the solution yet. But let's see what I find by using 12%. I plug in the present worth in the present worth formula, and I find that it is negative. Okay, so now I have a nice bracket, right? The solution is somewhere in between, and I need to find it. And you can see here, it's roughly halfway through, probably. I mean, that's kind of the guess, but not quite. I mean, just by comparing these two numbers. If I use linear or straight line interpolation, exactly like we did, so you can plug in the formula the same way, or you can rederive it every time, this is what you get. So this is your estimate now. It's 10.3%. Okay, so let me try that and see what I get. Because obviously I don't know if it's going to give me a present worth is equal to 0 because I'm still approximating. So let me try. If I plug in 10.3%, I get something that's fairly close to 0, but not quite. And remember, this is in millions. So like once you multiply, I mean, you're going to get what, 45,000, right? So it's still maybe not quite small enough. And so now maybe I need to do some more computations. I need to like iterate again. So let me actually adjust a little bit and try 10% instead of 10.3%. I get this value. So obviously now it's in between these two values. And I've narrowed it down like quite enough that maybe the next time I interpolate, I will get something that is very accurate. So if I do another round of interpolation, right, because I have a bracket now, I find that this is the value, 10.18%. Now if I plug in the present worth just to check if I'm close enough to 0, I get something that's maybe I'm happy with, okay? And so it depends on your tolerance, like when you stop. Because you may decide like 7,000 or whatever, or 10,000 is a good enough approximation, and you stop there, right? But there's maybe no need to do another round at that point. So it just depends on like what you're comfortable with and when you decide to stop. So here, this is practically 0, and so we may stop here. Now, if I use a computer, this is actually the value that I get. And notice here that we've gotten pretty close to the actual value. It's just a few like decimal places off. All right, and that completes this question, right? So that's how we find I using this trial and error method. The final approach is using software, and like I said, Excel can do this for you. There's a function in Excel. So there's a YouTube link which is like 1 minute or 2 minutes long, very quick. Basically, it's showing you how to use the function that's called IRR, right? And you specify a cell range, which is your cash flow, and an initial guess. You don't have to specify the guess because it has a default value, I think of 0.1, right? Because you have to start somewhere. So even sometimes software, they do sort of the trial and error. This is how they search. It's kind of like they try this. Oh, I've overshot the value, so I go back, I decrease, stuff like that, right? But they may be a little bit more intelligent, not exactly the way we did it, but the principle is kind of the same. And so you have to sometimes, I mean, it's beneficial to specify an initial guess, but you don't always have to. I've tried it with a few very simple cash flows, And as soon as I select the cells, it will give me the value. So it's very nice and very quick. You can also check your textbook on these pages. I hope this is accurate. I did not check this. Just to see another example, a more detailed example about how to use software, how to use Excel to find the internal rate of return. Okay, so now we know how to find the rate of return. Now our ultimate goal of this chapter, like the previous 2 chapters, is to know how to evaluate single investments and also how to compare different alternatives. But now we're going to use this internal rate of return criterion, which is different from, at least in approach, it is different from the present worth criterion or the annual equivalent worth criterion. So let's see what the relationship is between the internal rate of return and the present worth analysis. And we've already seen this in chapter 5, right? If you remember, we drew a graph that looks like this. And we said, well, first of all, what does present worth analysis say? Well, for a single project, if the present worth is positive, I will accept the project, of course, using I to be or as the MAR, right? And if it's negative, I reject. If it's 0, I'm indifferent. But you guys remember, we also did some like sensitivity analysis by changing I just to see like when would my decision change, basically from accept to reject. What value of I would make me change my decision? And at the end, we drew a graph that looks like this, right? So you start here, the present worth is high. Again, like we said just now, when we increase I, the present worth goes towards 0, so it decreases. And you see here, this function shape is nonlinear. There's a slight curve to it. And it, assuming this is a simple investment, right, it crosses the x-axis only at a single point. And so therefore, it does have an internal rate of return, and that is equal to the value, to the root, right, of this expression. And that is the I star value, okay? And what we saw before was the following. Of course, in this region here, my net present worth is positive. Obviously, every point here on this curve is above the x-axis. So here I will accept based on what I just described here. But then if you cross this I star, this internal rate of return, I'm in the negative zone. So here, everything is negative. So therefore, I'm going to reject my single investment. And so we stated this another way, and we said you can compare your MAR value, your I, let's suppose the MAR is here. So I here is MAR, to the internal rate of return. And we said if the internal rate of return is bigger than your MAR, or your MAR is smaller than the internal rate of return, then you accept. And so again, this is saying exactly the same thing, it's just a different perspective a little bit. We're approaching it from a different angle, but we're saying exactly the same thing, and everything is consistent with what we've said before. And I think we've also talked about this in chapter 5. So this is our starting point. Just to see some other graphs, again, if you have a simple investment, so project A, you guys remember from the example that I've showed you before, the rule is the following. I look at my MAR, and I look at where it is. Is it in this range? Is it in that range? If it's in this range, I accept. If it is in this range, I reject. It's very easy. And for a simple investment, it's very clear that it's going to be easy because, I mean, I only have one intersection point. I mean, life is good. Now, if you look at non-simple investments, the picture is a little bit more complicated. Because you notice here the present value is positive. Then it switches to being negative. And then it's positive again here in the range C, or in the sort of interval C, if you will, right? And then it goes back to being negative again. Now, intuitively, the way we defined MAR, if you remember what MAR means, like MAR is a minimum attractive rate of return, okay? So ideally speaking, I would like to have the following, right? If I increase my MAR, I want to have a threshold policy. I want to say, if my MAR is less than this threshold, I accept. And then as I increase my MAR, my minimum attractive rate of return gets higher and higher and higher. So therefore, basically, you need to convince me more about the investment in order for me to invest in that investment. And so I'm more likely to reject as you increase the MAR. But this is obviously not the case here, right? Because here, I first accept, then you increase the MAR a little bit more, then I reject, then you increase it more, then I accept again. So this is a little bit weird. Like, this situation is makes it a little bit unclear, and it doesn't fall nicely into our threshold policy that we want to adopt, right? And so for that reason, non-simple investments, they have their special case, and we're going to deal with them separately, okay? And so here's the flow chart that shows you what we're going to do. So let's assume, first of all, we have a single project. Again, so we're trying to decide whether or not to accept or reject a single project. If that investment is simple, what do I know about simple investments? I have a unique rate of return. And so I can take whatever I star that I find to be my internal rate of return. Okay, because it's unique. It's just one value. And then my policy is basically I'm going to accept the investment. Just to go back to the drawing, right? If my I star is bigger than my MAR is somewhere here, let's say. And that means the net present worth is positive, as we've seen in the picture, right? So this is what we've done so far. What about non-simple investments? Well, first of all, I know that it's possible that they may have multiple rates of return. Okay, it's not always the case. I can draw maybe, or I can use software. I can try my best to see if it does indeed have a unique rate of return. It may not always be very easy to see. Of course, if it does have a unique rate of return, then maybe I can still use this policy here. But let's assume, and that's why here it says generally, it doesn't say always. Generally, you will have multiple roots, right? Multiple values of I star. So you can't really pick one single internal rate of return. What do we do in that case? Well, there are two options. One is actually, and we're not going to cover this, but it's in your book. There's chapter 7a. It shows you a technique to find the true I star, the one value that you need to use. I'm actually not sure how it works because I haven't gone over it myself. But just know that it's there if you need it. What we're going to do here is basically abandon the internal rate of return approach and go back to our old friend, the net present worth criterion, because it's much easier. I can look at this graph. Instead of using this sort of threshold policy with internal rates of return, I will just evaluate the present worth. Is it positive? I will accept. If it's negative, I'm going to reject. Okay? So if I'm here, if I'm here, if I'm here, I just find the net present worth, and based on the point that I find, I will accept or reject. The last thing, since it's time to finish, if we have mutually exclusive projects, we're going to do something called incremental analysis. And we're going to see why we need incremental analysis. And basically, we're going to find I star for an investment that is B minus A. So we're going to take in project B, and project A, and do B minus A, subtract the cash flows, and then do some analysis on that. And then we have a similar policy type, right? Similar threshold policy. If my interest rate is bigger than the MAR, if the internal rate of return, is bigger than the MAR, I will select a certain project. If it's less, then I'll select another project. And we're going to see the details of that later. Okay, so I'll stop here. I'll take your questions after I stop recording. Otherwise, I will see you next class, inshallah.